Okay, let's look at this next circuit. Imagine we have an EMF, and this time we're going to have 3 resistors. R1, R2, and R3. This time, however, their configuration is a little bit different than in the previous example. So whenever we have this arrangement, and let me draw this a little more schematically, right? So whenever we have devices that are in this configuration, device 1, device 2, device 3, we say that these devices are in parallel. And so I drew in these 3 parallel lines to accentuate that. The important part is as with series, right? We have no intervening components. So, for instance, if I were to put a device in here, device 4, then if I were to do that, then device 2 and 3 are no longer in parallel. But interestingly, 3 and 4 are in series. Okay, so in order to be in parallel, the devices must have the configuration that you see here with no devices in between. We have some other terminology here as well. So we have positions here where three wires meet. And again, I could always soften the edges on the wires, on the wire here. Okay, so it's really one continuous wire. But in these positions where 3 wires meet, we have a special name for that point, and we call that a node, an electrical node, right? In contrast to nodes that we've met in wave phenomena, right? So a node is where 3 or more wires meet. Okay, so we have nodes here. All right. So that's an interesting twist on this electrical circuit. So let me redraw this. Let me redraw this circuit in a way that in a way where it is identical, right? So again, here's our EMF, and we're going to have resistor 1. Resistor 2, and resistor 3. And again, we have here 2 nodes, R1, R2, and R3. So what will happen here in this circuit, unlike in series, is that the current established, right? The current established, and I'm going to call this I total. The current here splits up into three currents. It's going to be the current going through I1, the current going through I2, and the current going through I3. And these currents will then recombine at this lower node, and out will come IT, the total current. So charge must be conserved. We talked about that way back when we first talked about electrostatics, is that the amount of charge in this total current must be equal to the total charge that splits up into these three branches. So we can say that formally, right? We can say that the total current is equal to I1 plus I2 plus I3, and we can formalize this a little bit better. So currents into nodes, we give a positive sign, and currents out of nodes, we give a negative sign. So we could have very easily written the above equation as IT minus I1 minus I2 minus I3 is equal to 0, which again gives us IT is equal to I1 plus I2 plus I3. And we say then, what we say is that the sum of currents at any node must be 0. Okay, and again, with this convention of currents into nodes is positive, currents out of nodes negative. And this then is called Kirchhoff's current law. Kirchhoff's current law. So let's use Kirchhoff's current law here to analyze this circuit. And so we need one more piece of information, and that's easily seen from actually either one of these diagrams. If we look at the voltage across the resistors, and again, remember here, wires are ideal. That is, that there's no resistance. So the voltage here is whatever the high side of the EMF is, okay? We'll call that V high. And the voltage here is actually, by convention, equal to 0. So again, with ideal wires, what that says is that the voltage across R1 is equal to the voltage across R2 is equal to voltage across R3. And actually, in our case, that's equal to script E. So what arises then is another important principle, that is for electrical devices in a parallel configuration. For electrical devices in a parallel configuration, the voltage the voltage across each device is identical. Okay? Again, that's an important principle. So we can take our circuit now. We can take our circuit, and we know that I total is equal to I1 plus I2 plus I3 by Kirchhoff's current law. And we can now use Ohm's law. Okay, so the voltage across R1 is going to be the current going through R1 times the current R1. Likewise, the voltage across R2 is going to be the current going through R2 times R2. And the voltage across R3 is going to be equal to the current going through R3 times R3. In which case now I1 is equal to VR1 over R1. I2 is equal to VR2 over R2. And I3 is going to be V over R3. So R3. That's going to be script D over R1. That will be the EMF over R2. This will be the EMF over R3. And we can plug these now, right? We can plug these into Kirchhoff's current law. And then what happens is that we get that I total is going to be then E over R1, E over R2, script E over R3. We can factor out the E. That's going to be E. This will be 1 over R1. It's 1 over R2 plus 1 over R3. And now if we think about what we did with our series circuit, we can think of now transforming our resistors in parallel to a single resistance circuit. But in this particular case, what we want to do is we want to preserve I total. So I total will be going through this circuit. Okay. And then by Ohm's law, or actually by Kirchhoff's, either by Ohm's law directly or Kirchhoff's loop law, we have E minus IT times R equivalent is equal to 0, where that E is going to be equal to I total times R equivalent, or I total is going to be equal to script E over R equivalent. So now if we look at, right, if we look at these two equations, this one and this one, if this is equal to IT and that's equal to IT, then they better be equal to each other. So we have E over R equivalent is equal to E times 1 over R1 plus 1 over R2 plus 1 over R3. The EMFs cancel from both sides, and we get that 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And we arrive at the recipe for determining what the equivalent resistance is in the transformed circuit. So let's just pretend, right, by way of example, that R1 is 1 ohm, that R2 is 2 ohms, and R3 is 3 ohms, what would the equivalent resistance be? Okay, well, we can easily figure that out. So 1 over R equivalent, 1 over 1 ohm, is 1 over 2 ohms, plus 1 over 3 ohms. Common denominator is 6, so this is 6 over 6 ohms, plus 3 over 6 ohms, plus 2 over 6 ohms, which is 9, 11, 11 over 6 ohms. Right? We're not done because we have that 1 over R equivalent is equal to 11 over 6 ohms. We have to take the reciprocal of both sides of that equation, which means that R equivalent now is 6/11 ohms. And I want you to realize that that's much less than 1 ohm, which was the smallest resistor in the parallel arrangement. Okay, so, and that's a general principle. The equivalent resistance will always be smaller than the smallest resistor in the parallel arrangement. Okay, beautiful. And in general, right, we can write that 1 over R equivalent is 1 over R1, 1 over R2, all the way out to 1 over Rn. We can write that in summation notation. So it'll be k equals 1 to n. So it's 1 over R sub k. Okay. So that's resistors in parallel, and it's also an example of a multi-loop circuit. And so we got a chance to see multi-loop circuits. Now, I want you to study examples in the book. So example problems 27, 27.02, 27.03, 27.04, and that'll give you some looking at some practice on using Kirchhoff's voltage law and Kirchhoff's current law in multi-loop circuits. And I won't spend any more time with that, and I'm pretty sure you did a laboratory on that as well. And hopefully you did that laboratory before we went into quarantine. Anyway, take a look at those example problems. All right, people. More stuff to come. All right, take care. Have a wonderful day today. Bye.